Hello dear students, this is Professor Amindradash from Achievers, and in this particular video I will be discussing about the solution of physical chemistry problems in the first phase of test 2 for CSIR NET. Okay, so I will be solving some important problems over here. This particular test was conducted on Unit 2, in which we had thermodynamics in physical chemistry, and you all know that thermodynamics is one of the most important chapters in context to physical chemistry for CSIR NET. A lot of questions come from thermodynamics in every NET examination for chemical sciences. So pay very good attention to this particular video and let's solve some very interesting problems in thermodynamics that I have given in this particular test. Okay, so at first let's move on to this very first problem. So let us read out the problem at first, line by line. Then we will make an attempt to have a solution. So you can see that the internal energy of a system at fixed volume is found to depend on temperature as Et equal to AT square plus BT to the power 4. Then what is the expression of entropy as a function of temperature? So what is given? You see, the first thing is fixed volume. This pertains to the fact that volume is kept constant. This is very important. Internal energy E or U, whatever it may be, it is expressed as a function of temperature. And what is the expression? The expression is given by Et equal to AT square plus BT to the power 4, where A and B are obviously arbitrary constants. Now what you are asked to do? You are asked to find out entropy as a function of temperature. Okay. So this is what you have to do. Now this is small, not small t, this is capital T. Kelvin temperature or temperature in absolute scale is conventionally expressed in terms of capital T. Okay. So let's try to attempt a solution for this. Now we'll start with the fundamental equations of thermodynamics. So what are those equations? The first equation is for no non-mechanical work and reversible process, we can write TdS equal to du plus pdv, which is equivalent to dE plus pdv. So this is the most fundamental equation of thermodynamics. It is the combination of first and second laws of thermodynamics. The two conditions have to be satisfied in order to validate this particular equation. Those two conditions are no non-mechanical work and reversible process. Once these two conditions are validated, this particular equation is valid. TdS equal to du plus pdv. Either you can express internal energy in terms of U or in terms of E. But in the question it is given in terms of E. So we'll use this particular equation, TdS equal to dE plus PdV. Okay. Now let us look into the condition that is applied for this particular process. What is the condition? The constancy of volume. It's an isochoric process, the volume is kept constant. And once the volume is kept constant, so this PdV part is reduced to 0. So TdS is equal to dE. Okay. Provided the volume is kept constant. Now one may ask a question that why we keep the non-mechanical work equal to 0, that means there is no non-mechanical work, and also why do we consider the process to be reversible. I mean to say, why these two conditions are valid. One may ask this question. Because it is not given in the paper, still we are considering that these two conditions are valid. Why? So in order to answer this question, at first you need to know that what is non-mechanical work and what is mechanical work. Mechanical work is normal PV work. If you apply force, there is a displacement. So F dot S. This is the definition of mechanical work. That's what happening over here. Non-mechanical work is basically it's a non-PV work. I mean to say that in case of a non-mechanical work, there will be no force, there will be no displacement. It basically occurs due to some interactions. I mean to say, suppose you consider a system, a multi-component system, and let us consider that the components do not react with each other, and say the multi-component system is homogeneous. I mean to say you have water, you have NaCl, you have KCl, you mix them together, they will mix up. So how does this mixing process carried out? How does this mixing process carried out? In order to carry out this mixing process, what happens within the system is that the solvent molecules will incorporate the solute molecules into their interstitial spaces. I mean to say, the solute molecules will find their positions in the intermolecular space that is furnished by the solvent molecules, and thereby it will create a homogeneous medium. So you see, there is an interaction between the solute and solvent molecules. The solute molecules are finding the positions within the interstitial spaces provided by the solvent molecules, and thereby there is no force on displacement type of work, there is no PV type of work. So this type of work is known as non-mechanical work, and that is possible if you are considering a multi-component system, but this is a mechanical system. This is a mechanical system. Nowhere in the question paper it has mentioned that this is a multi-component system. So one can easily interpret that this particular system is a mechanical system which is devoid of any non-mechanical work. So we can easily rule out the possibility of any non-mechanical work present in the system. So the possibility of non-mechanical work has been abolished. Now let us ponder into this particular condition, the reversibility of the process. How can we know that the process is reversible? In this case, you consider the parameters, those are asked in the question. You see, one is internal energy and another is entropy. So we are dealing with two parameters in the question. As per the question, we are dealing with two parameters. One is internal energy and another is entropy. Now what is the common feature? What is the common feature between these two thermodynamic parameters? What is the common feature between these two thermodynamic parameters? The most common feature between these two thermodynamic parameters is that both of them are state functions. Both of them are state functions. And what is the fundamental or rudimentary criteria of being a state function? What is the rudimentary criteria of being a state function? It is necessitated that a state function is essentially a path independent function. A state function is essentially a path independent function. So a change in state function, when a process is carried out, a change in state function solely depends on the initial and the final value. On the initial and the final value. It is independent. It is independent of the path. So it is immaterial whether the path is reversible, whether the path is irreversible. It's immaterial in case we are considering or dealing with a state function. So in this case, we are dealing with state functions, internal energy, entropy. They are independent of the path. They solely depend on the initial and the final states, since they are state functions. So it is not important whether the process is reversible or whether the process is irreversible. It doesn't depend on that. So we can consider the process to be reversible. That makes no difference in case of a state function. That's why we can consider the process to be reversible. It doesn't make any difference. Okay. So that's why we have considered the most fundamental equation in chemical thermodynamics over here, TdS equal to dE plus PdV, which is supposed to be the combination of first and second law of thermodynamics, and thereby we have applied the condition of constancy of volume that is provided in the question paper, and thereby we end up into this particular reduced form, TdS at constant V equal to dE at constant V. Now one can write del S del A at constant V is 1 by T. So at constant V, ds equal to dE by T. You can write it in this way. Simple. Now what is dE? AT square plus BT to the power 4. This whole thing is divided by T. If you carry out this division, you will get AT plus BTQ. Okay. So this is the expression of ds. Now you ought to integrate it indefinitely. If you integrate it indefinitely, you will get the result. So you are integrating both sides indefinitely. I had made a mistake over here. Let me correct it. Let me correct it. You got ds equal to dE by t. The mistake I made was I substituted the expression of E in place of dE. It was not like that. It's d of E. What is E? At square plus bt to the power 4 divided by t. Okay. Now a being a constant is pulled out of the differentiation. Differentiating t square, it becomes 2t dt. Again, b being a constant is pulled out of the differentiation. Differentiating t to the power 4, we get 4t cube dt divided by t. Now this t cancels out, it becomes t square. So it becomes 2a dt plus 4b t square dt. Okay. The mistake I made in previously was I substituted E in place of dE. That was wrong. Okay. Now the same thing. Now you have to integrate it indefinitely. So 2a, it's a constant pulled out of integration. 4b is again a constant pulled out of integration. So you get this. So you get s equal to 2at plus 4/3 bt cube plus some integration constant s naught. S naught is the constant of integration. Okay. Now, how can we find out the value of S naught? How can we find out the value of S naught? You see, at t equal to 0, entropy is 0. This is coming from the third law of thermodynamics. By third law of thermodynamics, we are already acquainted with the fact that at absolute 0, the absolute value of entropy is reduced to 0. At absolute 0, the absolute value of entropy is reduced to 0. This we know directly from third law of thermodynamics. Obviously, there is some exceptions. We know the concept of residual entropy is there, but in general, for thermodynamics, for third law of thermodynamics, we will abide to this condition that at t equal to 0, S is 0. Now, if you apply this condition, you see S equal to 0 and t equal to 0, you will find that S naught is 0. If you apply this condition on this particular equation, obviously you will find that S naught is 0. Okay. Now, if S naught is 0, then S becomes 2at plus 4/3 bt cube. Okay. So you see, this is option number C. Clear? Very simple. Very simple, but you need to know the conditions, you need to apply the conditions on the fundamental equations. Okay. So this was my first question that I have discussed over here. Let's now move on to the next one. This one is a very interesting problem, this one. You see, the entropy of a thermodynamic system as a function of energy is given by the following graph. Basically, this graph expresses entropy as a function of energy. It expresses entropy as a function of energy. Now, there are three phases. This is phase A, this is phase B, and this is phase C. Now, you have to calculate the temperatures of these three phases. So, how to do this? Students, this can be done right from the previous problem. We have already found that del S del E at constant V is 1 by T. Okay? This is known to us. I have already arrived at this particular condition in the previous question that I have discussed right now. We have already arrived at this particular condition. Okay? Now, see, here you have plotted S along y-axis and E along x-axis. So, this S is y and this E is x. So basically, this is del y del x. What is del y del x? It's the slope. So for a curve plotted on AC plane, the slope is 1 by t. So this 1 by t is the slope. It is del y del x. Del y del x is nothing but the slope. So for a curve drawn on AC plane, obviously 1 by t is going to be the slope. Okay. So slope of A is 1 by TA. Slope of B is 1 by TB. And slope of C is 1 by TC. As simple as that. There are three regions, three phases, A, B, C. And slope of every phase is given by 1 by the corresponding temperature. So slope of A and A is 1 by Ti. Slope of B and B is 1 by TV. And slope of C is 1 by TC. So this is absolutely clear to all of us. Okay. So if this concept is absolutely clear to all of you, then it's very easy to solve the problem by directly pondering into the picture. So let's contemplate. Let's contemplate into this particular diagram. You see, in this case, the slope is increasing. The slope is increasing. So what happens? This is positive. This is positive. Here, the slope is 0 because it is parallel to x-axis. So MA is 0. MA is positive. And what about MC? MC is also positive. MC is also positive. So both of these are positive. But you can see the slope of MA is greater than that of MC. Why? Because this phase A is steeper than the phase C. It is quite evident from the given diagram that A is steeper than C. A is steeper than C. And as A is steeper than C, it's quite evident that MA is greater than MC. So both of them are positive, but this MA and if MC they are compared, then we can say MA is greater than MC. Now, if MA is greater than MC, then obviously TA should be lower than TC because TA and TC both are situated at the denominator. So it means basically 1 by TA is greater than 1 by TC. That means TC greater than TA. So I found TC greater than TA. TC greater than TA. And what about TB? If 1 by TB is 0, that means TB is infinite. So TB is highest. It's highest. Out of these three temperatures, which one is the highest? Obviously TB is the highest. So TB is way greater than TC and TA. So from this logic, one can write that TB greater than TC greater than TA. So TA is lowest, then comes TC, then comes TB. So C is the correct option. Okay. So this is also a very interesting problem, The logic is del S del E at constant V is 1 by T, and where from this logic is coming? I discussed this logic already in the previous problem. So I already have arrived at this particular logic in the previous problem. We acquainted with that and we started from that. Okay. Now students, let us move on to a final problem for today's video. This is also a very interesting question. You see, the free energies of n particles in a volume V and temperature T is F equal to n kBT ln N naught V kBT whole to the power 5 by 2 divided by N. So this is the form given. What is F? F is nothing but Helmholtz free energy. We also conventionally write it as capital A. So either it is denoted as capital F or capital A as per the thermodynamic conventions. So this is quite evident. This is known to us. So the expression of F or A is given. From here you need to find out the expression of E or U, internal energy. Now how to do that? So at first let us jot down the fundamental equations. Okay. So at first we will be penning down the fundamental equations, then we will apply. The first equation is F equal to E minus Ts. This comes by definition. And now differentiating dE minus dds minus s dt. Now for any reversible process with no non-mechanical work, same condition, dE minus TdS is nothing but minus PdV. Because TdS equal to dE plus PdV, we have already done this in the first problem, very first problem I have discussed. We have already done this, that TdS equal to dE plus PdV under the constraints of no non-mechanical work and reversibility of the chemical process. So we are already acquainted with this condition that dE minus TdS is minus PdV. So I am not repeating it over and over again. We are already acquainted with this fact. So one can write dF equal to minus PdV minus SdT. So from here we can say that del F del T at constant V is minus S. Obviously, it is quite evident. If we divide dF by dt at constant volume, then obviously this PdV term will be abolished and the result will be minus S. So this is my equation number 2. If you combine these two equations, what we are getting? F equal to E plus T multiplied by minus S. In place of minus S, we will be substituting this particular parameter, del F del T at constant V. So it becomes E plus T multiplied by del F del T at constant V. Now in the question paper, you are asked to find out the expression of E and F is given. So E should be equal to F minus T del F del T at constant V. So you have to use this particular expression. Okay. So this is our working form for this particular problem. This is our working form. You are given the expression of F and you need to determine the expression of E. Okay, so this will be the working form. We have already reduced this working form, and in due course I have also explained what are the constraints. Now it's simple. At first, let us find out the value of del F del T. So if this is F, F equal to N kBT multiplied by ln, you just bring out all the terms together and leave out T. I mean to say, you see, you can expand it in this manner, ln AV, A naught V, kb to the power 5 by 2 divided by n. So all the terms excluding T is included in one bracket of logarithm, and the exclusive term for temperature dependence is 5 by 2 ln T. So you craft out the temperature dependent term out of this jumbled term and let all the constants be together in a single term. Yes, V is also constant. Why? Because we will be applying the condition of constancy of volume. That's why V is also constant. So all the constants are gathered together, collected into a single term, and T is crafted out. So in this way, the process of differentiation will be easier. Now del F del t at constant v. What is this? N kb is a constant. So N kb is pulled out of the differentiation, and we'll be applying UV method. So this is U and this entire term is V. So when we'll be differentiating U, V will be kept constant. So if t is differentiated with respect to t, it's just 1. So we'll just write the V term, ln a naught V kb to the power 5 by 2 divided by n plus 5 by 2 ln t plus. Now you are differentiating V. Upon differentiation of V, the first term will be reduced to 0, so it's a constant. So you will be left out with 5 by 2 ddt of ln t, that is nothing but 1 by t. So it's 5 by 2t multiplied by this t. Okay. Now you recombine these terms together once again. What will happen? Again it will become ln a naught v kbt to the power 5 by 2 divided by n. Just recombine these terms together using the property of logarithm. We'll find this. Okay, as simple as that. Now let us substitute the values. Therefore E equal to F. What is the value of F? F is n kbt ln a naught v kbt to the power 5 by 2 divided by n minus t multiplied by this parameter n kb t is multiplied with this parameter, and let's remove the bracket. So ln a naught v kbt to the power 5 by 2 divided by n minus n kbt multiplied by 5 by 2. This parameter is left out, 5 by 2, so we do that. N kb multiplied by 5 by 2 multiplied by this temperature with a negative sign. So you get this. And these two terms are happily cancelled out. These two terms are happily cancelled out. These two terms are happily cancelled out. So you are left out with 5 by 2 n kbt. You are left out with 5 by 2 n kbt. See? So this is the correct answer, 5 by 2 n kbt. Okay. Let's look into the steps once again if there is any problem. There is one problem with this entire process. We are getting E to be equal to minus 5 by 2 n kBT. But absolute energy cannot be negative. Absolute energy cannot be negative. So you must take the magnitude of this. And the magnitude of this is 5 by 2 n kBT. That's why the answer is 5 by 2 n kBT. We are getting a negative sign, but we know that absolute energy, absolute thermodynamic parameter, it can never be negative. That's why we'll be taking the magnitude, and it's 5 by 2 n kBT. So that's all, students, for now. Thank you and bye-bye.